Alright, welcome to the video. Today I'm going to be talking about parametric form of a conic section. So the objective is that you should be able to identify the conic section in parametric form and convert it to standard rectangular form and possibly even graph it. If you've already done graphing conic sections in standard form, then you're ready for that part. But let's take a look at what we're doing on this video. Alright, so here we have the standard rectangular form of a circle, an ellipse, and a hyperbola. Just so you know, I'm not going to do a parabola because a parabola is easy. You just see a t squared in there. You know that we have a parabola. We've done those before. So these are the ones that we often see is a little bit different. So the parametric form of a circle looks like this. X equals R cosine t plus h, and y equals R sine t plus k. We can see what h and k are here. Remember that r is the radius and h and k are the center. Okay, so this is kind of a nicer way because we can see that h directly, we don't have the opposite here. We see that h directly goes left or right and k goes up or down. For an ellipse, notice here the r's are the same. Well, the nice thing about the ellipse that we can see in the difference is just that they have different numbers in front. Specifically in this case, A and B, and that has to do with the length of the, the vertical or horizontal, they're not really radiuses, but the distance from the center on the going left to right and the distance from the center going up and down when we graph an ellipse. For a hyperbola, those are a little bit different here. We're not going to use sines and cosines. We're actually going to use secants and cosecants. So A secant t plus h and y equals b tangent t plus k. That would be for this hyperbola here where it goes to the side, and then for the one that goes up and down, we're going to have x equals a tangent t plus h and y equals b secant t plus k. And b always goes with y here, and a always goes with x, so that way you don't, so this you don't have to ever really figure out which one's which. The only difference is here is the left or right one goes with secant, and then the up and down one goes secant with the y, secant with the x, and I'll show you kind of why that happens in just a second. So let's take a look at how are we going to get, how do we get from here back to rectangular form. Now I think that the easiest way to do it is just to recognize what's going on. Like if you can recognize that this and just easily convert it, that's fine, but I want to show you how we get that using eliminating the parameters. So let's, oops, went too far. Let's just take a look at a few of these and eliminate the parameters. So, alright, so we're going to go with x equals r cosine t plus h, y equals r sine t plus k, and I'm going to first subtract h and subtract k, so I'm going to have x minus h equals r cosine t, and y minus k equals r sine t. Square everything. So I'm going to have x minus h squared equals r squared cosine squared, and y minus k squared equals r squared sine squared. Add them together. It's kind of like I'm adding straight down here. R squared cosine squared plus r squared sine squared, and a factor out an r squared, and this is the Pythagorean identity, which is just saying this is just 1, so I'm going to get x minus h squared plus y minus k squared equals r squared. Alright, so now it works, so we see how we get the rectangular form of the circle. Now we could do the same thing for the ellipse, only for the ellipse I'm going to divide r over first and then square both sides and then add over. Maybe you can try that on your own and see if you can do that. Let me show you the hyperbola though, because that one's kind of interesting here. Alright, so here we have the hyperbola, so I'm going to subtract h over just like I did with the other ones. And a lot of the work here is the same, and I'm going to actually divide a over as well. So I'm going to divide a, and I'm going to divide b, and I'm going to get it equal to secant t, and this one going to be equal to tangent t. Now I'm going to square both sides. Okay, so I'm going to square everything, and I'm going to get x minus h squared over a squared. Oh, it's starting to look like this formula here. Y minus k squared over b squared. Looking kind of like our formula. Except in this case, we're not going to add, we're going to subtract, because the identity that we have for our Pythagorean identity for secant and tangent is that secant squared minus tangent squared is equal to 1. So I'm going to subtract now. So x minus h squared over a squared minus y minus k squared over b squared is equal to secant squared minus tangent squared. And I know that this is 1. So then we get our hyperbola formula. Squared. Alright, so this is our formula for hyperbola. So this is how we would eliminate the parameter. But let's take a look at some problems that you'll have to do. So identify the graph. So you just look at this picture, or I'm sorry, you look at these parametric equations, and you notice that you're dealing with cosine and sine, and you have two different numbers in front of your cosine and sine. So you automatically know that this is an ellipse, and this is an ellipse with a center at 1, -4. Now if I wanted to convert this into the rectangular form, I would just go x minus 1 squared over 5 squared is 25 plus y plus 4, because remember I'm adding 4 to this side, squared over 100 equals 1. Now one of the advantages of having it in parametric form is that we can see exactly how many units we're going to go and stretch it in the y direction. And we can see directly 1, -4, that's going to be our center. So 1, -4. And we can see directly that this is going to go up 10 units from there. So up 10 units is going to get me to 6. Down to 10 units is going to get me down here at 11, 12, 13, 14. And then we've got 5 units, and that's another, like I said, this is an advantage of using them parametrically, because we can see exactly how far to go. We don't have to take a square root or anything. So then we're going to, I'm not very good at drawing these ellipses on this pad. It looks like a rotten potato. But there you go, that's our ellipse. Okay, so let's take a look at this one. We know we have a secant and a tangent. We know that the secant always comes first. So this is going to be an x minus 2 squared. It's going to be an x minus y, which means it's going to go left and right. So we're going to do the same thing. We're just going to start with our center, which is going to be -2 and 1. And then our, this is A and this is B, so we know that our asymptotes are going to be at 5 over 3. So up 5, 1, 2, 3, 4, 5 over 1, 2, 3. And there's our asymptote. And then down 1, 2, 3, 4, 5 over 3. There's our other asymptote. And this is going to go left or right. Okay, so it should start here, go out this way. Start 1, 2, 3. I went too far. 1, 2, 3. Should go right here. Okay, so I went too far on this one. It should start right here. It goes 1, 2, 3 units. Okay. So it tells us exactly how far to go left and right from here. All right. Okay, so here are a couple of practice problems for you to try. Make sure you try them and see what you can get, and then at the beginning of class, if you want, I can go over these. Okay, see you later.